In section 2.1, we introduced the idea of a limit using slopes, the relationship between secant slopes and tangent slopes. But now that we're actually jumping into limits, and we're going to talk about the definition of a limit and some different ways to compute limits, you need to get the idea of slope out of your head. That was only one very specific example, and we're not actually going to talk about slopes anymore this chapter. We'll talk about slopes a lot more in chapter 3, but limits are not slopes. That the slope example we saw in 2.1 was just one very specific example that we used in order to introduce the idea. What we will do in 2.2 is I will tell you exactly what a limit is, and we'll do a bunch of examples, and I'll show you a bunch of different ways to calculate limits. So just kind of an informal definition. Math definitions sometimes are kind of tricky to read, so I'm also going to have a little graph to go along with this, hopefully to explain it a little bit better. So let's say we have some function f of x. And it becomes arbitrarily close to L as x becomes arbitrarily close to A. Then we can say that the limit as x approaches A of f of x equals L. So this is the notation that we are going to see for our limit problems. And it is read, the limit of f of x as x approaches A is L. So A is going to be a number. When we actually look at some examples, we'll have a number in that spot. F of x will just be some function that they give us for that problem. So there will be a function in that spot. And our answer, L, will also usually be a number. So what exactly does this mean? There's a whole lot of letters in there. So let me show you on a graph what exactly this means. And graphically is a common way to calculate these limits. So let's say we have the graph for f of x. And we'll say here is x equals A. So A is a value on the x-axis, and L is a value on the y-axis. So as we start to get really, really, really close to A, so here is A. As we get really, really, really close to A on the x-axis, either coming from the left or from the right, the y value is getting really, 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 really close to L. So technically, all we're doing is identifying a location on the graph. Now, that point doesn't actually have to exist, because all we're doing is we're looking at what it appears is happening on this graph. We're not actually calculating a function value. We're just saying, as we get close to A, what does it look like is happening to the y value? So as x approaches A, what does it look like the y value is approaching? So one of the most important things to point out is the answer to a limit is a y value. You will be given the x value here, and you will be given the function. And what we're being asked to find is the y value that it looks like that function is approaching. Sometimes there will be an actual point there, and sometimes there might not be a point there. So let me show you another example where we could still do a limit and there is no point there. So let's say this is our f of x, and there's actually a hole at a. And that's actually okay when we do limits, because when we do limits, we're just approaching a. We're not actually looking at the point itself. We're just saying, if we approach a, what does it look like the y value is approaching? So when we approach a, it looks like the y value is approaching L. So even if there is a hole in the graph, we can still do a limit. So holes are okay when we do limits. Now, both of these graphs that I've just shown you, I have approached A from the left and from the right. There is a little bit different of a notation we might see if we don't need to approach from both directions. And those are called one-sided limits. So we could just be concerned with what it looks like when we approach from the left, or what it looks like when we approach from the right. So there's a notation that goes along with that here in our limit notation that would tell us only come from the left or only come from the right. So if we were to see the limit as x approaches a, and then a little minus sign as a superscript, so it's in the exponent position, but it's not an exponent. It's called a superscript. This means we are only concerned with what's happening in our f of x function as we approach a from the left. So the reason the minus sign means left is because on a number line, minus usually means smaller. Usually when you subtract, your values get smaller. And on the number line, smaller numbers are to the left. So if you see the little minus sign in that superscript or exponent position, that means we're only concerned with analyzing what's happening to this function as we approach from the left. So with that in mind, if we want to only approach from the right, so if minus means left, plus means right. So if we see a little plus in that spot, we want to know what is f of x approaching. As x approaches a from the right. If you don't see the plus or minus, then both sides have to agree. They have to be approaching the same number. So when these two limits match up, so when the limit as x approaches a from the left is equal to the limit as x approaches a from the right, So both of those end up equaling the same exact number. Then we can say that we actually have a true limit, and it's not a left limit or a right limit, that it's an actual true limit as x approaches a. So we don't have a left or a right. It's doing the same thing when we approach from the left and we approach from the right. We got an answer of L in both directions. That means the limit for as x approaches a for f of x is L. If we were to get two different answers when we were to come in from different directions, then we would say that the limit does not exist. So let's add that as well. If the limit as x approaches a from the left does not equal, let me add my f of x here. If it does not equal your limit as x approaches a from the right, then we would just say that this is a limit we can't do, because it looks like it's approaching two different things depending on which direction we're coming in. And we don't want to say two different answers. We want one definitive answer to this limit problem. So we would say that it does not exist. And let me show you an example on a graph of what exactly this would look like. These are typically piecewise functions. So here's our A. And I'm going to say that's 3. That's 1. That's 2. And these two pieces combined make up f of x. F of x is a piecewise function. So the limit as x approaches a from the left for this function. So here's our a. So if I follow this graph from the left, it looks like it's going to approach a y value of 3. So we would say from the left, this answer is 3. But if we do the limit as x approaches a from the right on this function, so follow the graph in from the right, it looks like it's approaching a y value of 1. So there is no definitive answer as to what is happening on this function at x equals a. From the left, it looks like one y value. From the right, it looks like a completely different y value. So what we would say is the limit as x approaches a for f of x does not exist. And that's because our left limit and our right limit, which we can do, but they're not equal. They're two different things. So holes are fine. So what we saw up here are holes are fine because they're approaching the same number on both sides. So that's why holes are okay. But what's not okay are these big gaps in between. This graph has a big old gap in between where we completely jump y values. On the left it's at 3, on the right it's at 1. So that limit would not exist. So graphically, to calculate a limit graphically, we are just following our graph and getting really, really, really close to the x value that we're asked to find. And then once we get really close, we're looking to see what the y value is. The answer to a limit is the y value that it's approaching. We can do this from the left or from the right. If there isn't specifically a left or right, then it's got to do the same thing from both sides. So let me show you one more graphical example. And I'm going to put actual numbers on this graph instead of just A's. And we will use this graph to do several limits. So this graph goes through the point -4, -2. And then -2, 0. And then it jumps up, it jumps up to -2, 2. And we have an open circle there. And then we've got -1, 3 with another open circle. And 0, 2. And 1, -1. And then we've got 2, -2 with a closed circle. 3, 0 with an open circle. And then we have got a flat line going out at 2. So it's a pretty complicated graph. This is our f of x. And this would definitely be a pretty ugly piecewise function if we were trying to write out the function notation for it. We're going to do a whole bunch of limits for this graph and talk about what they are and why they are what they are. So the first one we are going to do is the limit as x approaches -4. The limit as x approaches -4. So they've given us the x value, and when they ask us to do a limit, we are trying to identify the y value. Now this one doesn't say left and right, which means we need to do both of them and make sure they agree. So here's -4. If we follow that down to the graph, we want to make sure that when we approach from the left and from the right, the two pieces of our graph are connecting, and they are, so that's good. That means our left and our right limits are going to agree, and we want to follow that across to the y value. So it looks like on this graph, as x approaches -4, y is approaching -2. The limit as x approaches -2 from the left for this function. So I'm going to get rid of some of these highlighters. Oops, that's not what I wanted to do. That's good enough. Now we want the limit as x approaches -2 from the left only. So here is -2. And I want to know what's happening on this graph as we approach -2 from the left. So there is -2 from the left. I want to know the y value that it's approaching. So if we follow that y value back to follow that graph back to the y-axis, that is a y value of 0. Now let's do the limit as x approaches -2 from the right on this graph. So again, here's our -2, but if you find the piece that's to the right of -2 and you trace it to the y-axis, that's going to hit a y value of +2. Now if you look at those together, what does that mean for just the regular old limit? The limit as x approaches -2 for f of x. As we approach from the left, it's 0. As we approach from the right, it's 2. So the limit as x approaches -2 of f of x, without the left or right designation, that means that this limit does not exist. Without the left or right designation, they've got to match up. And we're going to look at one more set really quick. I'll keep my graph in view. We're going to do the limit as x approaches -1 from the left. And we're going to do the limit as x approaches -1 from the right. And try to figure out what that means for the limit as x approaches -1 in general. So from the left and from the right, and then based on those two answers, we can come up with just an overall answer for the limit as x approaches -1. So here's -1. If you follow that up to the graph, we want to approach from the left, and that looks like a y value of 3. We want to approach from the right, and that also looks like a y value of 3. And because they're matching, that means we actually have a limit there. As x approaches -1, the limit for f of x is 3. And that matches up with what we said earlier. Holes are fine. Holes are perfectly fine when we do limits. What's not okay are these big gaps. When we have those big gaps, limit does not exist. When we have holes, no problem. So this is how we do a limit graphically. If we have the graph, we can find the x value that they're asking us about and look and see what is happening with the y value. And we have to make sure that the y value is doing the same thing from the left and from the right, unless they specifically tell us only do the left and the right. So this is how we do it graphically. Now, even if you're only given the equation, even if you're only given the function, you can type the function into your graphing calculator and take a look at the graph and do the limit graphically. So graphically is always an option, whether you are provided the graph or not. You can always type the function into your calculator and do it graphically. Another option is to do these limits numerically. So what we did just by kind of traveling along the graph, we can do in a table with numbers, which takes a little bit longer. but it is useful sometimes if the graph is really crazy or we can't tell what the nice numbers are. If the numbers are kind of crazy, have radicals or something in them. So numerically, if we wanted to calculate a limit, what we're going to do, think of what we did here. We were given an x value. The answer to a limit is a y value, and we'll know the function. So we're going to just be plugging x values in. Now, we don't actually care what the point is there, and sometimes we won't actually be able to plug that point in. The function might be undefined there, like when we have a hole. We just care what it looks like it's approaching. So we're going to be plugging in numbers that are really close to the x value that we're given. And I plug in numbers, and you're going to see most textbooks plug in numbers that get closer and closer by a power of 10. So we're going to plug in numbers that get closer and closer to the target x value. By powers of 10. So what I mean by this, and the easiest one to do is 0. And I'm not going to give you a function for this. I just want to show you an example of how the table would be set up. If we wanted to do a limit as x approaches 0 for some function. Now it doesn't say left or right, which means we have to look at the left and the right. So what I like to do when I set this table up is I like to put 0 right in the center, because I'm approaching from the left and the right. I like all my numbers to be in order. So I'm going to put 0 right in the middle, and I'm going to put the numbers to the left of it on the left and the numbers to the right of it on the right. Now, I am going to move away from 0. Now, this is what we're trying to calculate. This is going to be our limit. We're trying to look at some other values and the pattern that we get in the other values to figure that answer out. So I'm going to move away by 1 power of 10. And I don't mean 10 and 100 and 1,000. We want to be really, really, really close to 0. So we're going to actually do, and let me include this, negative powers of 10. So we're going to do negative powers of 10 because we need to stay really, really close to 0. So plugging in 10 and 100 and 1,000 and 10,000, that's not going to give us any clue as to what's happening at 0. We need to stay really, really, really close to 0. So if I move 1 negative power away from 10, 10 to the negative 1 is a tenth. So when we move to the right, we add. When we move to the left, we subtract. So adding a tenth would give us 0.1. And the tenth is actually the farthest away that we want to be. We want these values really, 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 really close. So this is going to be 10 to the negative 1. And then we're going to get a little bit closer. So that's going to be 10 to the negative 2, which is 100th. And then 10 to the negative 3, which is 1,000th. And we're adding these because we're going to the right of 0. And then we're going to do the exact same thing to the left of 0. I am just making mistakes left and right here. I'm sorry. There we go. So we are going to subtract a tenth. That's going to give us negative a tenth. And then we're going to subtract a hundredth. And then we're going to subtract a thousandth. So if you look at these x values, we're approaching 0 from the left and from the right. We're getting really, really, really close in our top row with our x values from the left and from the right of 0. Now what we need to do, if we have a specific function that we're given, we will take these x values and we will plug all of them in to our function and figure out what y value is linked to them, what their y coordinate is. And we'll plug it here. And then we will see, all right, what pattern do I see in these y coordinates? What are these y values approaching in the middle? And that's our limit. So we're always adding or subtracting these negative powers of 10 to our target number. So our target number we get from the question, and we want to get really, really, really close by adding or subtracting these negative powers of 10. This is the basic setup for the table when we do limits numerically. And then once we have the basic setup for the x's, from there it's just plugging into the function. Now you can get those y values very quickly with your calculator if you plug your function into your y equals. So I would say y1 equals your f of x, and I would put my table in ask mode. So if you go to your table settings and make your independent variable independent, I think it says INDPT, put that in ask mode. Then when you go to your table on your calculator, you can type in what x values you want. Typically your x values in your table always go by whole numbers. And we definitely are not using whole number x values here. We want some very specific x values. So if you put your table, if you put the independent variable in your table in ask mode, then you can type in the specific x values you have and it will pop out the y values that go with it. And you won't have to calculate every single one of those by hand. So let's actually do an example of this. I didn't have a function for that one. And this is going to be one that we can't just necessarily plug our number into to see the answer. We have to look at the numbers around it to figure it out. So we're going to do the limit as x approaches 2 for x squared minus 3x minus 2. No, plus 2. All over x minus 2. So I want to know for this function, x squared minus 3x plus 2 over x minus 2, this is our f of x. What is happening to the y value on this graph as x gets close to 2? Now usually when we're interested in a y value, we would just take the x value and plug it in. But if you try to do that here, if you just plug 2 in for the x's, you get 0 over 0. 2 squared is 4. 3 times 2 is 6. And then plus 2, all over 2 minus 2. That's 0 over 0. 0 over 0 is a problem. That's called indeterminate form. And we'll talk more about that in the next section. indeterminate form of 0 over 0, it does not equal to 0 because the top is 0. It's not undefined because the bottom is 0. It really means nothing. It means we've got to fix it. And then the next section, we'll talk about some algebraic ways that we could possibly fix this. But for right now, we can't just find a y value by plugging an x value in. So we could look at the graph, or we could make a table. So what we're going to do on this one is we're going to make a table. And this is the numerical way to find a limit. So our target value here is x equals 2. So I'm going to put that right in the center. And we're trying to figure out the y that goes with it. And I'm going to move away from 2 by negative powers of 10. The farthest we're ever going to move away is a tenth. So if I add a tenth, I get 2.1. So a little bit closer than that is only adding a hundredth, so 2.01. And a little bit closer than that is only adding a thousandth, so 2.001. And then we're going to do the same in the other direction. So here I added. This way I'm going to subtract. So now if I subtract a tenth from 2, I get 1.9. If I subtract a hundredth, I get 1.99. And if I subtract a thousandth, I get 1.999. So I've got some values really close to 2 here, and I want to know what this function is doing at values really close to 2. And maybe we can look at the pattern in those values in order to make a prediction at what is happening at 2. So this is where we have like a lot of little tedious computation work to do, or we can go to our calculator. And I'm just going to pull out my calculator here. Unfortunately, I do not have a calculator on my screen that I can pull up, but I will work on that. So I'm going to go to my graphing calculator, and I am going to type in x squared minus 3x plus 2 in parentheses, divided by x minus 2 in parentheses. I'm going to type that into my y1. And then I'm going to make sure that my in my table settings, which is second window, I'm going to make sure that my independent variable is in ask mode. If it's not, just use your arrows to highlight ask and hit enter. And then it should change the highlight from being on auto to ask. Then I can go to my table, and most likely your X and Y columns are going to be blank because we put it in ask mode, meaning that your calculator is waiting for you to tell it which X values it wants to calculate Y values for. So I'm just going to type all these in one at a time now. So I want the Y value that goes with the X of 1.9. So I'm going to type in 1.9, and it gives me back 0.9. And then I'm going to type in 1.99, and it gives me 0.99. And then 1.999 is 0.999. And then jump to the other side, 2.001 is 1.001. 2.01 is 1.01, and 2.1 is 1.1. You should be trying this along with me, and if you are not getting the same numbers, make sure that you have your function typed in with parentheses around your numerator and parentheses around your denominator. Because there is addition and subtraction in your numerator and your denominator, they need their own set of parentheses. That is the number one mistake that I've seen people make when they're not getting the correct answer. So if you're not getting the same answers as me in your Y, check to make sure you have it entered correctly. So now we know what the Y's are doing around 2, and then we want to use them to make a prediction of what's happening at 2. So if we follow them in from the left, and if we follow them in from the right, where does it look like they're going to meet in the middle? Wherever they meet in the middle is the answer to our limit. And it looks like they're going to meet in the middle at 1. We've got 9/10, 99 hundredths, 999 thousandths, 1 in a tenth, 1 in a hundredth, 1 in a thousandth. These numbers are getting really, really close to 1 in the middle. So we're going to say that the limit as x approaches 2 for x squared minus 3x plus 2 over x minus 2 is equal to 1. So this is how we do it numerically. We're actually looking at the numbers in a table. Now the only difference, and the last thing I want to add to this, is if we were to ask to do a one-sided limit numerically, then we would only have to set up half of this table. So if we were asked to do the limit as x approaches 1 from the left, then all I have to do is subtract my powers of 10 from 1. I don't have to include the addition side if all we're interested in is what's happening if we look from the left. So our table, when we set this up, 1 is not going to be in the middle, 1's going to be out here at the end, because we're only interested in approaching from the left. So we're going to subtract a tenth, so that's 0.9, subtract a hundredth, subtract a thousandth. So for these one-sided limits, we only include half of the table. Or if we wanted the limit as x approaches, let's say -5 from the right. If we're approaching from the right, then -5 is the smallest number. So I'm going to put -5 here at the beginning. And then we're going to add a tenth. That's the farthest away we're going to get. If you add a tenth to -5, that's going to take you to -4.9. And then add a hundredth and add a thousandth. These are values that are bigger than -5. These are values that are to the right of -5. So for one-sided limits, numerically, you only have to set up half of the table. That's the only difference.